Alright, so this tutorial is going to summarize some of the key concepts that we brought up yesterday when we were introducing the laws of motion. We discussed what it means, the difference between moving and not moving, what it takes to move, what does it take to not move, and we came up with some pretty interesting conclusions. Essentially, we came up with conclusions that are completely counterintuitive to what one would expect. So this tutorial is to kind of give a little history of what humans have thought for over a few thousand years to kind of make you feel a little bit better about yourself and that what you're thinking is extremely common. It turns out to be mostly wrong, but that's all right. We need to be aware of what we're getting wrong before we can start replacing it with what we're getting right. So we'll reinforce this more and more with other lessons, but let's get down to the essentials. So we're going to go back to about 400 BC. We mentioned the other day Aristotle. Okay, he was really the first person, at least in Western civilization, to start not only thinking about this, but writing down some principles that were taught to other students. And they were based on a combination of casual observation and common sense. So when Aristotle looked around him at the world and in terms of motion, he basically reduced it to two basic types. All right, one was natural motion, and the other was, I'm going to put forced motion. I know in class you used the word violent, but let's just use the word forced. So natural motion is simply this: objects naturally want to be not moving. Okay? In other words, all objects resist moving. If you leave them alone, they will not move. Very simple. Okay? Whether it's something small, whether it's something large, mountains, a mosquito, marble, if you leave them alone, they don't want to move. However, if you force them, okay, and to force them means you need a contact force in order to move. Okay, so if something's sitting there and I push on it, I pull on it, then it's going to start moving. As soon as I take away that force, that push or pull, then it comes to a stop. And we see that with most everything. There are some exceptions that which we have to address. Okay, so take away the force and the object will go back to its natural state of not moving. All right, so the examples we gave in class, you all more or less agreed with this because, again, with casual observation, this is what you primarily see. But there were some exceptions to this. One was falling bodies. The other was heavenly bodies. Okay, so we address this. Aristotle had to explain, well, why do objects fall? There's nothing in contact that makes them fall, so why do they do that? And he basically said things fall, so they go back to their natural state of not moving. Because when something's done falling, it's resting on the ground. For heavenly bodies, that's a little bit more difficult. Essentially, as we said, that Aristotle explained the motion of the sun, the moon, and the planets is, well, they're in the heavens, and the heavens don't obey the same rules as here on Earth, so they just naturally move. That's what heavenly bodies do. So he classified them under natural, even though they didn't quite fit the idea of his original natural motion. So as we mentioned, whenever you start making exceptions to a rule, that probably means there's a flaw in your rule. And that flaw is usually going to be fatal, but perhaps not. Okay, so does this make sense? Is this logical? Does it fit our experiences? I would answer, and you should answer, yes, yes, and yes. 99% of the public thinks along these lines because that's what we experience every day. However, things start to get a little bit more dicey when you start asking the following. So what if we had, so this is after Aristotle, we moved through medieval times and even through the Renaissance. We're talking over 1,000 years of thinking about this. Yeah, there were the Dark Ages and we didn't necessarily worry about motion too much. But for the natural scientists who want to understand it, we have to explain something like, let's say, an arrow flying through the air, or a ball rolling along the ground, or a wheel. Okay? The question we have to ask is, what keeps them going once after we've pushed them? Okay, so if my hand is not in contact with it anymore and I throw a ball or a string and an arrow propels an arrow forward, why does it keep going? The old answer was something called impetus. All right, today you might use the word momentum. Okay, And so what we're thinking, we're so biased into thinking that if something's moving, there has to be something pushing it along. We invented this concept called impetus, which is kind of like a residual push from the original contact force. Okay, a memory of some sort. And if you really stop and think about it, that's kind of odd. It's like a ghost-like force that's a remnant from our original push or pull or whatever. Okay, and so you might ask, well, you know, all right, so an arrow's moving through the air. Why does it eventually slow down? Well, people would just answer, it runs out of impetus. They don't explain how it runs out of impetus or why it runs out of impetus. They just know that certain objects will take a little bit longer to slow down than, let's say, a desk across the floor. So they just attribute it to this thing called impetus. You guys would say it just runs out of momentum. So does this fit our experience? Yeah. Is it logical? Kinda. Does it make sense? I'm going to put a question mark there, because you stop and think about it. How does one get a memory of a force? How does an object know that it was pushed 10 seconds earlier? All right, so you can, again, we can start thinking about this. Kind of makes sense, but there's some problems with it. So it wasn't until the early 1600s, so we didn't talk about this in class, but the key was made, and it was by really the father of modern science, and that's Galileo Galilei. Okay, and he gives us something called the Law of Inertia. We'll talk more about inertia in class, but let me just sum up what this took him a long time to really figure out, and he never really fully appreciated it. And it wasn't until Newton, about 100 years later, that finally put it all together. He basically says objects do not need a cause to not move. We understand that. In other words, if an object is sitting still, it will remain sitting still if we leave it alone. However, the key was, he says objects do not need a cause to continue moving. In other words, if an object is rolling along the ground, it doesn't need anything to keep it rolling. It will continue to roll and roll and roll and roll. And that's an odd concept because we rarely see that. Okay? Basically, what we're seeing is, and we've talked about this class, that not moving and continue to moving are really the same thing. There's no difference. You cannot feel the difference between moving at a constant speed and not moving. If you were to wake up in an airplane and look out the window, you wouldn't feel yourself moving, you'd see the ground going by. In fact, it's impossible for you to do any experiments to determine whether you're flying through the air or you're hanging from an elaborate setup in Hollywood where it makes it seem like you're flying. There's nothing you can do to distinguish the difference. Okay, we know that here on Earth. On Earth, we think we're not moving out to the Earth, yet we know that the Earth is moving through space. We can't feel the difference because they're the same thing. So if you ask what pushes the Earth around the sun day after day after day, it's not gravity. Gravity does something else. It's nothing. So if an object is moving, what's pushing it along? It could be something, but it doesn't have to be. It's usually nothing. So what this is important is, in other words, impetus does not exist. Momentum does exist, but momentum means something else, and it's not how we normally apply it. And so Galileo said the natural state of something is to not change. Okay? If you leave something alone, the object will continue doing what it's already doing. If you want to change what it's doing, then you must bring in a force. Okay? So forces are required to change motion. Forces are not necessarily required to make something move that's already moving, and we'll make the distinction there. So you might ask, why did Aristotle, one of the great thinkers of all time, and countless others, we're talking over 1,000 years, get this so wrong? There's a lot of reasons. A lot of it's bias. We see things always not moving and not realize why that is. But the most important thing is he never ever considered the influence of something we'll talk about in much greater detail, friction. Okay, so we'll pick up from there, and eventually we'll start quantifying the rules for how forces affect changes in motion.